Okay, hey everybody. I hope you're doing okay. I hope you're staying safe. I hope you're staying sane and checking out on your family and friends. Hope you're being productive and all that good stuff. And so we're going to do another lecture for acoustics here. And today we are going to talk about diffusers and diffuser design. So let's see. We're going to talk about some different types of diffusers here, but before we do all that, what do we need diffusers for? And one of those things is Flutter Echo. I imagine you've experienced Flutter Echo before. Just that idea of successive repetitive reflections that happen really quickly. It's not a good thing because it actually, particularly in the studio, because it degrades our sense of pitch if we have that. Again, remember the Haas effect. Remember that anything outside of that 30 millisecond window, we perceive as separate reflections. So it's in that ballpark of that, probably that 30 milliseconds oftentimes. From the standpoint of studio design or trying to eliminate Flutter Echo, yes, we can do something as simple as splaying the walls 5 to 10 degrees. That will cut down on the direct reflections that happen back and forth between walls, but probably not to the extent as some well-designed diffusers. And we're going to take a look at what that is in just a few minutes. So if I try to, this spot actually isn't really good, but somewhere over here, once in a while I can hear. I don't know if you can hear that where the microphone is, but you can hear that boing, ring, 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 ring. That just boingy, nasally, echoey sound, and that's an okay example of Flutter Echo, at least as best as I can do here in my living room. And so part of what we want, what we're focused on is with diffusers is direct reflections and Flutter Echo and things like that. So diffusers are used to minimize strong specular reflection. So what is a specular reflection? And so a specular reflection is anything like that looks like this, where the angle of incidence equals the angle of reflection. Just like, I assume most of you play pool. It's kind of the idea. And this is what's going to happen if we have a hard surface most of the time. And frequencies enter angle of incidence equals angular reflection, and they reflect what we say specularly. And so this is what happens naturally with the smooth hard surface, and this is what we want to have happen with the diffusers, so that the sound is splayed out in all directions so as to avoid Flutter Echo and boingy reflections just bouncing back and forth and things like that. Okay. Here's a graph that shows us actually a number of cool things. Let's start here in the middle with reflection. So we have a hard surface, we have the specular reflection like we just talked about. We can look at that in this graph both from a time response. That's what's happening here. So we have the initial sound, and then we have the specular reflection, and that specular reflection on a hard surface looks about the same. It's delayed, and it doesn't have really any attenuation or anything like that. And here's what that looks like from a spatial response coming in like this and bouncing out. There's a little bit of fanning out, but not very much. If we look at what happens when we have some absorption, some sort of absorber on the wall or something like that, again, we have this temporal response that looks about the same, but it's attenuated greatly because of the absorber. And then we can look at what that looks like spatially. Again, there's still the same idea of probably a little bit of specular reflection happening. It's just greatly attenuated, again, compared to the reflection. And then what we want with diffusion is something that looks like this, where we have this incoming signal and then it's splayed out hemispherically like this. And so we get this nice diffuse breakup of the signal that's very hemispherical. And also, so not just what's happening spatially, but from a temporal response or a time response. See what happens, and we're going to talk a little bit about why this happens a little bit later when we look at diffuser design, is that we get a delayed temporal response that looks like a nice reverb tail, right? And so we get some time delay as that signal is broken up. So how do diffusers work? And two basic methods. One is from a random scattering, just any sort of rough surface, any surface with texture or with some surface variation is going to have some sort of diffusion. It's not going to be predictable, but it can have very useful diffusion. And then second is by a design diffuser that possesses what we say all necessary grading spaces. We're going to talk about what that is in just a minute, to ensure that the diffraction, it's uniform diffraction, and it's even and evenly spaced out diffusion. So quick story just in terms of this whole idea of, and a couple examples about this idea of just random scattering diffusion. So back when I was living in Nashville, I bought this Lavery A to D to A converter just online from who I thought was a random dude. And as is the case in Nashville, it wasn't a random dude. I went to this guy's house and it was just a very, mediocre house in a very mediocre neighborhood. And you walk around to the back where he told me to enter. And lo and behold, there's this addition in the back of his house that's huge. And boom, it's F. Reed Chippen, who is a Grammy winning mixing engineer, one of the just literally the best mixing engineers out there, killing it and has been for years, as well as Grammy winning engineer producer. Here's his beautiful SSL, and then behind it you can see he's got this really cool, it's a really simple idea, not super expensive. He's got bookshelves behind his SSL with books, but the really cool thing was you can't as much tell with the black and white picture, but all the books are turned so the spine is facing the bookshelf, not out like we usually are. So it's all basically for the most part, white pages. You see these white pages, and it's just acting as a reasonable diffuser behind his console there. Here's actually the other side looking behind his console for facing the other direction. You can see he's got bookshelves and the same idea. Now, how effective is it? Obviously it's effective enough for him to keep winning Grammys, so I'm not going to knock it. If we varied the size of the books and how much space there was between them, then we could make this, actually take this idea and make it more diffuse from a technical standpoint, probably. But again, who am I to argue with Reed and his Grammys? So, but it's a really cool idea. It's not that expensive, so maybe think about that as one way to combat problems in your room. And then here I'm quarantined just like you. So here's another example. This is me actually walking back to my home studio. And when I redid my home studio area a few years ago, this is a wall that I did that, again, not just to look cool, but for the purposes of trying to create some sense of diffusion. I just took tons of drywall mud and just splattered it as thick as I could along this wall. And it was fun and messy. And I don't know if you can really get a sense of it, but there's places on this wall that this stuff sticks out at least a half an inch, if not maybe as much as a 3/4 of an inch in places. And so what does that mean in terms of diffusion? What does this just rough surface variations like this, and we'll say to a half an inch, how far does that get us in terms of fusion and diffusing what frequencies? Well, again, much like we've said all semester, the idea of the quarter wavelength is super important. And so typically it's the idea is that if you to be effective for diffusion purposes, you have to be the quarter wavelength of the frequency that you're trying to diffuse. But even as much as an eighth of the wavelength is going to have some sort of scattering. It's going to be maybe not as effective as a more equal diffusion that you see at the quarter wavelength, but even something that is as much as an eighth of the wavelength of a frequency is going to have some scattering functionality to it. So if we do some quick math and we go back and again, like I've been trying to hammer into your head all semester, this idea of 1K is 1 foot long. And so if we do some quick math, and I'm not going to write it all out, but if we do some quick math and go to inches and I start talking about a half of an inch, then that half inch or 3/4 of an inch of variation on this wall is going to get me effective diffusion down to at least 5K, but certainly I'm going to get some scattering down into the 3.5K region, which is actually, if you think about it, if we're recording vocals in there, recording drums in there with a lot of cymbals, that's going to be really helpful. So not just pretty, not just cool looking, but effective. Another wall in my studio here, another back wall in the studio is this really cool sandstone fireplace. And it's really rough cut old sandstone. I don't know if you can get a sense through the pictures how rough cut and how much variation there are in these blocks, but there really is, certainly I would say at least 2 inches, 2.5, maybe or more certain places. That's how much variation depth there is in that sandstone. And I tried to get some pictures to illustrate that, but I don't know if you can see it or not. But again, if you think, if we go back, we do some quick math, then if I have 2.5 inches of variation, then I'm going to be getting, again, down, and on this wall, I'm going to be getting down to maybe 850 hertz in that area. So I have diffusion from 800, and for a wall like this, I'm going to have pretty effective diffusion from 850 hertz up, which is pretty cool. So now let's go back, let's jump to the other idea, not just random, unpredictable diffusion, but something that is mathematically calculatable and we're able to predict from a frequency standpoint and a quality standpoint. And so Schroeder is actually the guy that we credit a lot of this stuff to. He did a lot of experiments starting in 1975 with this idea of a maximal lake sequence, which you're going to look at in just a second, and then a quadratic residue diffuser, which is really the most common diffuser we see in studios these days, and you'll recognize those once I show you a picture of those. They're great for small rooms. We see them, like I said, we see them in studios all the time, and tracking rooms, both tracking and mixing rooms, but also in large auditorium, particularly for ceilings. And so again, if I go back a few years to when I was living in Nashville, it was when they were building the amazing world-class Schermerhorn Symphony Center and for the Nashville Symphony. And they went and traveled orchestra halls all over the world and did comparisons and listenings and took evaluations and how much people liked the different orchestra halls and all of this and whatnot. And basically what they found out is that, you know what people really like? They like something that's really akin to a shoebox in shape, that's pretty narrow and pretty long. And because there's something really pleasing about the sidewall reflections that you get for something like that, but not from the upper reflection. So what they do is they keep the walls fairly narrow, they make it a deep space, and then on the ceiling they do some sort of diffusion, because when there's too much interaction from upper reflections, it's not as appealing to our senses, and I don't know the exact reason for what that is, as apparently side reflections. So we see diffusion on ceilings of concert halls a lot. I think we saw diffusers on the ceiling of the bridge studios that we looked at in depth when we were looking at the studio construction stuff. So Schroeder gave us our QRD diffuser, which is quadratic residue diffuser. There's another diffuser that's similar mathematically called a primitive root diffuser, but they're just not quite as effective. They're similar, but not quite as effective. And so we're just going to focus on QRD diffusers today. So here's this idea of an MLS diffuser, a maximal length sequence diffuser. And basically it's a binary profile, meaning there's just two, there's a 0 and a 1, or two different profiles. And we're not going to go through the longhand math of what this is what this looks like in one dimension. This is what some of they might look like as a 2-dimension MLS diffuser. And the problem with anything that's designed out of this MLS sequence is that it basically only covers, you can design them, but they're only really effective for over about a 1 octave range. So what would that be? You could design one and it would be effective maybe kind of from 500 hertz to 1K, or you could design one that might be effective from 1K to 2K or something like that, but it's not going to be effective over a broad frequency range like you can with a quadratic residue diffuser. And so, math! Again, kind of like the math that we did for the inverse square law. I'm showing you this so you know what it's derived from. We're not going to do this math in class. You're not going to do this on a quiz or a final even or anything like that. But a quadratic residue diffuser is a method for designing a multi-level diffuser that operates over a greater wavelength range or a greater frequency range than an MLS diffuser. This math, I don't know, I guess just to say, is based on D sub n, which is depth based on an integer number of depths that we're going to talk about. Wavelength not divided by 2 times p, which is a prime number, s times s sub m. And s sub n is the sequence defined by n squared modulo p. Okay, what is all that? It basically means all of these components of well width, well depth, and a prime number sequence period are all related together and are going to allow us to design a diffuser that has an upper frequency limit, a lower frequency limit, and a quality based on how these things interact. Okay? And how about we just leave it at that? Okay? Here's just a drawing of a typical QRD diffuser that kind of shows us the profile of different depths. Now, this is a pretty big one. This one could be based on, again, they're based on prime number sequences. So what is that? 5, 7, 11, 13, 17, 23. This could be like based on a prime number of 23. We could take a second and probably count and figure it out or something like that. But that's what that is. We have the well width, the well depth, and the period. Here is just a drawing of, again, of those same ideas. This is the pretty typical design. You hopefully, I'm guessing maybe you've seen this a number of times. We see, this is the prime number sequence 5. This is what this looks like if you use if you have a QRD design that's based on the prime number sequence of 5. Again, a prime number sequence of 5 is not going to have as even or as high a quality diffusion as one that's based on a prime number sequence of 17 or something like that. And so this is one period. Here we see this has this prime number sequence of 5 with 3 periods, okay? And what that would look like over 3 periods. We'll see this same design probably a couple more times. Here's just somebody doing a basic homemade QRD with wood. We'll see some other homemade QRDs later. Just a quick note on that is if you're going to build one, and I've had a number of people build these. I've built some myself. I've had a number of people to build these for their projects in acoustics class. And just be careful. They get so much heavier than people realize really quick. And so if you're making something like this, you have to have massive mounting system to mount these on the wall. So be really, really careful of this type or the other type of QRD that people make, the 3D one. Because they get so heavy if you use heavy duty wood like that. And yeah, well, I'm gonna keep moving on. Here's a purchased one, and you can see here we've got them both going vertically and horizontally, vertical, 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 horizontal, horizontal. And basically the reason for that is when you have one-dimensional QRD diffusal like this, it only splays out or diffuses sound in one direction. So anything coming in here like this to this middle panel is going to splay and diffuse things out hemispherically like this. And then anything coming in like this is going to splay out hemispherically like this. And so that's why they have these both vertical and horizontal here. So why does this work? What is happening? And so here is a basic 90-degree specular reflection off of a hard surface. And like we said, things, whether it's 90 degrees or whether it's coming in 45 and leaving 45 specularly, sounds are just immediately bouncing off and reflecting. So multiple things happen when we have a QRD diffuser. We get a phase shift, and so what's that? So if we have full length wells like this and they're interacting together, then we have this wave plus this wave was going to equal this wave that's greater in amplitude. But if we have these two, this phase shift is going to, as these add together, they're going to give us this less intense frequency wave. And then we get this time shift and the time that it takes to go from here to here versus going to here. And that's what gives us part of that nice decay of the reverb tail that we saw with the diffuser. And then we also get a spatial shift in the bounce that happens from all the different angles and bouncing off of angles. And so we get a phase shift, we get a time shift, and a spatial shift. And we put all of those three things together. It looks maybe something like this. Here's our, again, this is our QRD based on a prime number system sequence of 5. And so how does all of this work? The diffusion factors are a function of three main things, A, B, C. Three things. A, the well width determines the upper frequency limit of the diffuser. So the narrower the well, the higher frequency it will diffuse. Okay, we're going to look more specifically at that in just a second. But the well width determines the upper frequency limit. The well depth, the deepest well in the sequence, determines the lower frequency limit. So the deeper the well, or the deeper the diffuser is, the lower it's going to have an effect on lower frequencies. And the narrower those wells are, the more it's going to have an effect on higher frequencies. And then the higher the prime or num sequence, whether it's again 5, 7, 11, 13, 17, the higher we go, the more even it's going to be spaced out, the more smooth the diffusion will be with throughout the whole audio frequency spectrum. Okay, so here's what that looks like, what we just talked about. A, the well width determines the upper frequency limit. B, the well depth determines the lower frequency limit. And C, the prime number sequence that we're talking about, determines the quality of the diffusion. So let's go one step further in all of that. The maximum well depth should be 0.5 times the wavelength of the lowest frequency of operation. So maximum well depth should be 0.5 times or half a wavelength of the lowest frequency of operation. So half a wavelength. So let's say, let's go back to our reference that we like to use all the time. A 1K frequency is 1 foot long. So if we want to have a diffuser that's effective down to 1K, then we need to be half of that wavelength or 6 inches. So if I have a QRD diffuser that's 6 inches deep, then that's going to be effective down to 1K. Okay, and it's not going to be very, so you would say that it's diffused down to 1K if it's 6 inches deep, and it scatters maybe down to about 500 hertz, and then isn't really effective at doing a whole lot below that. Okay, the well width should be half the wavelength, 0.5 the wavelength, half the wavelength of the highest frequency of operation. So again, if you want to have a diffuser that goes very high and is good and effective at diffusing high frequencies, then we need to have an increasingly narrower well width. Okay, and so let's see, we'll say let's do some quick math. 4K. If we do if we want to effectively diffuse 4K, and so we say a 1K tone is 1 foot, a 2K tone is a half a foot, a 4K tone is it would be 3 inches, right? And that means 3 inches. If we want to be effective at 4K, we need half of that wavelength of 3 inches. That means our well width, if our well widths are 1.5 inches, then it's going to be effective up to 4K, but it's not really going to be any effective above 4K, all right, if we have 1.5 inches wide well width, okay? And then the highest frequency to lowest frequency define the operating bandwidth of the diffuser, okay? So let's see, what do I have here? Well width. The well width of the wells determines the high frequency cutoff frequency as 1/2 wavelength. That's what we just went over, okay? Period width. Period width, okay, hang on here, is the width occupied by the well sequence, or that. So if I have a prime number sequence 5, I have that pattern that we just looked at here. That's the period width, okay? You can do it longer than that. Here, we can do this one. That's the period width, C, okay? And that has to be at least equal to the wavelength of the lowest frequency diffused. And that would make sense if I add this and at least double the design depth. So if you think of the design depth, again, if I'm going to say that I want my diffuser to be effective down to 500 hertz. Well, a 500 hertz wave must be 2 foot long. If a 1K tone is 1 foot, a 2 foot wave, 500 hertz wave would be about 2 feet. And that means that my depth of my diffuser needs to be half of that wavelength. And so that would be 1 foot. So I need a diffuser now that's a foot deep, okay? A foot deep, and that's effective to 500 hertz. But let's look at this again. It has to be at least equal to the wavelength of the lowest frequency. So that means that my period, or my overall width of the diffuser itself, needs to be at least 2 feet. Okay, that's what these things put together mean. If that's not the case, then the well is too narrow and the lowest diffusion frequency will be higher than the design frequency that you put together. All of these things work together, okay? Effective distance. How far away from a diffuser do you have to be for it to be effective? Minimum seating distance for the interference patterns to fully develop. So all of those things that we talked about, the temporal, the phase shift, and the volume shift change, all of those things to happen to fully develop into a diffuse field is 3 times the longest wavelength diffused. So let's go back to what we just talked about. We designed a diffuser that was 500 hertz, right? For it to be effective down to 500 hertz. And so that means that the 500 hertz wave was 2 feet long, our diffuser was a foot deep, and has to be 3 times the longest wavelength diffused. If that wavelength was 2 feet, then that means we need to be 3 times that, or 6 foot away. So if I have that behind my console, as long as I'm sitting, and I have a diffuser I want to be effective down to 500 hertz, as long as I'm sitting 6 feet away from the wall, then that diffuser is going to be effective for me, okay? There is this idea of a diffusion coefficient that when diffusers are designed, or products are being evaluated for diffusion, just like absorption coefficient and just like other things we're going to see in the future. There's a diffusion coefficient, meaning if it's evaluated at 1.0 for a frequency, then it is a perfect diffuser at that frequency. If the diffusion coefficient is 0.0, then it's a perfect angle of incidence reflector. It means it's not diffusing anything. It's just whatever angle of incidence is angle of exit. It's going to reflect specularly, okay? So just a couple more things we're going to make today quick and call it a day. So based on all of those limitations of being narrow defining the high frequency limitation and being deep defines the low frequency limitation, we've got this idea of a diffractal diffuser or a fractal diffuser, which is basically a diffuser in a diffuser. So if you take a look, you can see here this large scale diffuser. And this is, again, actually, I think based on our prime number sequence of 5, yep, that we've seen a couple times today already. And so these depths here, this depth and this width, this depth and this width, is designed to counteract low frequencies. And so again, I don't know what the real size of this to scale is, but you know, if that's a foot deep, then you know, this could actually be useful, like we just talked about, for down to 500 hertz. But then on top of that, so we have a diffuser and a diffuser. So each one, in the back of each one of these is these mini diffusers that are then helping diffuse the high frequencies. So the overall large design is diffusing low frequencies, and then these tiny little diffusers in the bottoms of the wells are diffusing the high frequencies. I think if you think back to the construction thread that we did, some of the trim was custom routed with these diffusers, and I think it was even this five prime sequence, similar to this, that they had grooved into their trim, so that even that trim that was going around the edge of their bass traps, if I remember right, had a diffuser for high frequencies built into it. Here's just a closer look, cross section of this diffractal diffuser, where we can see the large scale diffuser and then the small scale diffuser for the high frequencies inside of it. Here's what we've been seeing more of lately than the one-dimensional QRDs, and this is a QRD in 2 dimensions. The same idea, but just in 2 dimensions, okay? And then there are all sorts of, actually, yeah, I didn't do this earlier. There are all sorts of, the reason I'm not gonna have you do longhand math with this is, again, like the room mode calculator that we talked about when we did room modes, and the absorption coefficient charts. I mean, you can just find resources readily available online for this. And so if we come here, I just, again, did a quick search, and then you can put together these, say what frequency range do I want my diffuser to be, and you can calculate it out, or you could say, this is what I'm going to design at, what frequencies is it going to be affected at. So if I do a really generic, super wide well width and depth of, let's not even 9 inches is deep, let's actually take it down, 6 inch deep, 3 inches wide, and a prime number sequence of 5, what does that turn out to be? And this will tell you how deep they need to be. And that pattern that we've seen repeatedly, 0, 1, 4, 4, 1, has to do with the depths proportionally of those wells, and that's going to be effective at 900 hertz to 2K. That's not super effective. Let's take and make this a 1/2 inch, and we'll do a foot, 12 inches. And we'll do it based on a prime number sequence of 11. Here are the depths, okay. Residue, that has to do, I didn't talk about that when we say QRD, quadratic residue. It's the remainder of when you take that integer number and the remainder that you get when you subtract those out. Again, I don't want to go into that too much because we're not going to do that math, and I don't want to confuse you, but that's what that residue is. And so by changing our dimensions so that we were 1/2 inch wide was our width and 12 inches deep, we now go down to, like we talked about before when we were just doing quick math, right? We're just under 500 hertz, and now we go all the way up. By the time we make their well widths only 1/2 inch wide, they are effective to up to 13K. The problem is that it's hard. Well, the reason we see diffractals is that it's hard to effectively build one that's really narrow and really deep at the same time, which is why we see the diffractals, or the diffuser and the diffuser. But there's a number of these things. QRDude is the software you can download. Same thing, it'll tell you there's frequency, number of wells, how they get laid out, what it looks like, the scatter frequency, the diffuse frequency like we talked about, and width and all of that good stuff. And so there's tons of resources out there to be able to do this, or to just punch in some numbers and see what you're going to end up with. If we take that idea one step further, There are also calculators out there for the two-dimensional ones. And so you plug in, you see a chart similar to this, and you're going to get numbers like this. And then each one of these is assigned a depth. And so this is depth 0, this is depth 1. And anytime you see a 1, you're going to place the whatever that depth is for the 1 in there. Whatever the depth is for 2, you're going to place those blocks that are that deep every place there's a 2. That's what all of that is. And so this is based on a prime number sequence of 17. It's a pretty comprehensive one. When we build them cheaply like this, we might call them an inverse QRD or a Skyline diffuser. And here's a homemade one. Again, I made these. I've had a number of students make these for their final acoustics project. Again, be careful if you build it like this. They are going to be so heavy and they're super hard to mount on the wall. So I've seen people do them out of styrofoam insulation, like hard insulation foam, and then spray paint them. And that's very effective and way lighter. Probably makes more sense. Just to go back though, when we see the wells, this is called a fin that has the division here that we don't see when we do this. And not to say that this isn't effective, because it is effective, but the fin makes it a higher quality diffusion because of the way that each well has its own specific place and how all of the different angles that it creates is more effective when there's the individual fin, and that goes for the one-dimensional QRD or the two-dimensional QRD like this. Now, the diffuser of all diffusers, the granddaddy of all diffusers, the mind-blowing phenomenon that is the master diffuser is Blackbird Studio C. I'm assuming that you've seen, that's pretty pixelated. Sorry about that. I blew it up a little bit too much. But a massive, massive, massive QRD diffuser that actually it's similar, I think, like we talked about QRD, but I think it's the other one. We'll see that in just a second. Let's look at a few pictures here, and I've got a nice little rundown. So 3 feet deep, that's how deep those walls are of those diffusers. Those diffusers are 3 feet deep. Amplitude modulated prime 181 and 769 1D primitive root sequence. It's the primitive root math, not the QRD math. Very similar idea though. What does that mean? That means that there are 138,646 different block heights. 138,646,000 different heights. That is massive. Ouch. Wow. The ceiling is 7 feet deep, and it's basically a diffractal. So you can see, take a look, you can see the large scale QRD diffuser happen, and then the smaller scale, like the rest of the walls on top of that. So that's diffusing super low frequencies up there. And 12 by 13 primitive root diffractal. And so there's 24,000 different block heights in the ceiling. And then the corners are a damped metal plate shelving resonators, curved with binary amplitude diffusorbers. So let's unpack just a couple things there real quick. One, there are the binary plates. So like we looked at for very early on, these things right here. So there's a metal plate that probably looks very similar to this that is stuffed with insulation. So it's a diffuser and an absorber in the corners. Binary amplitude, and so it's a diffusorber because it's a diffuser and an absorber, okay? And just a few more pictures so you can see, kind of try to look in there, all of those different, again, that's a lot of math. And if you don't know who did this, George Massenburg is the person who designed this room, who crunched out all that math, designed this and did this. George Massenburg, if you don't know, is again, multi-time Grammy-winning engineer, amazing, amazing engineer, who also gave us, that whole idea of the parametric EQ that we use on a daily basis every day in the studio. He designed the parametric EQ for us and gave us this monstrosity. He is a mad genius. So yeah, a few more pictures. There you can see the scale of it with a guy standing beside it right there. They recently turned this room into an immersive Dolby Atmos room, like what Miles is going to be teaching the immersive audio this fall. And so they've got huge ATCs, not only, I don't know if they have 7 of them around, but multiple ATCs in the ceilings to do immersive sound. So yeah, go check that out. One more thing real quick. Here you can just see some diffuser gobos. This is, I think if I remember right, it might be Skywalker sound, where they can set up some gobos. Again, they want to think of the idea of the speaker when we talked about speaker design and construction. If you take and you just hold a woofer in free space without a baffle, it's not going to create very much sound. We need the interaction, the separation from the rear of the sound. We need that interaction. Maybe to some degree we can say that's why it might be a good idea to have something like this. If they're in a giant scoring stage like this and they're a smaller ensemble, then they want the interaction of the sound that they're making coming back and developing a little bit more in and around themselves. And so that they've got these huge diffusers that are built onto these gobos, as you can see, are kind of cool. One more thing. Oh yeah. Here is what's called a diffuser block. It's made by, I think the company's RPG. Make a lot of standard studio diffusers and whatnot. I think you can probably buy a bunch of them at Sweetwater. But they make this construction block, like a cinder block that's made, it's actually not just a diffuser, it's a diffuser and an absorber. So we can see the diffuser pattern on here, but also that has these grooves with an absorptive material that gets placed into the grooves when it gets set. And those are panel absorbers, like we talked about when we talked about absorption last time. And so they're actually really absorptive down to like 25 hertz, I think, but then they're effective at diffusing as well. Here's, you can see what that looks like on a wall in an auditorium or something that's built. All of that's the cinder block construction. And so it's, instead of doing acoustic treatment afterwards, it's all part of the construction process. And so that's pretty cool. And I think that's it. So again, you should be finishing up right now your discussion board on absorbers and absorption coefficients, and then be getting started on, we'll have a discussion board on this. We'll ask a bunch of questions and talk about this a little bit more in depth in the coming days. So again, stay safe, stay connected to your family and friends, and I'll talk to you soon. Bye.